Hello. The last item in searching is a special kind of search, a search in game playing. You have a position, and your job is to figure out which move you should make in that position. Before I talk about that, I want to give you some idea on where we stand in a lot of the games that people play. As long ago as 1994, the program Chinook beat the world champion. He had been unbeatable for 40 years. That program has an in-game database which has the perfect play for all positions with 8 or fewer pieces on the board. There are 443 billion plus such positions. Now, this isn't the way game programs are done today. This was an early concept, and what it basically did was put in a lot of knowledge and take advantage of the fact that it had a lot of space to store those perfect moves. In 1997, IBM wrote Deep Blue. There's a little background story to this. The world champion had made a wager that no computer would be able to beat him in a match for 10 years. He won that wager, but he refused to renew the wager. He figured that the computer was going to break through in the next 10 years. I believe that champion was Tophoff, not the champion that I'm referring to in 1997. Deep Blue beat the world champion Garry Kasparov in a 6-game match. Deep Blue searches 200 million positions per second, uses a very sophisticated evaluation, and can go 40 moves ahead. There are very few humans who can look 40 moves ahead. There may be a few, but I'm certainly not one of them. In Othello, people refused, and sometimes that's called 5 in a row. Or actually, it's a game where you try to get as many of your color pieces on the board as possible, and you can flip over a line of your opponents by blocking him on both sides. In Othello, humans refuse to play against computer games because the programs are too good. Now, chess has approximately 10 to the 70th or 10 to the 80th possible positions. That's an awful lot. You're not going to look at every one of them. However, China, many, many years ago, invented the game of Go. It's played on a 19 by 19 board. The Chinese and the Japanese disagree on which country plays it best. Don't get in that argument. There are 10 to the 170th positions in Go. Now look, 10 to the 80th for chess, 10 to the 170th for Go. Go is by far a more complicated game. Most people thought Go was maybe a decade away from being really succumbing to computers. They figured that it just was too complicated and we needed larger computers before we could do it. Well, that didn't work. I copied this from a website. I have the site there. 5 years ago, AlphaGo played a match against the reigning three-time European champion. AlphaGo won the first ever game against a Go professional with a score of 5-0. AlphaGo then competed against legendary co-player Mr. Lee Sedol, the winner of 18 world titles. He's considered the greatest player of the past decade. AlphaGo's 4-1 victory in Seoul, North Korea was watched by over 200 million people worldwide. As I said, it was a decade ahead of time. Now, that isn't the end of the story. AlphaGo in 1917 was beaten. That's what the Go board looks like, by the way. I played it. There's an whole etiquette. You're supposed to hold your stone. Those are called stones in a particular way, and they're supposed to make a particular sound when you hit it. It's a very gentlemanly game and very interesting game. This fellow is a little concerned that we may be getting close to the Terminator. What happened is that a newer version of AlphaGo beat the old version and beat it badly. And here's the catch. The AlphaGo new version learned it on its own. It's a product of deep learning. That means it didn't have to be given fancy algorithms for how to evaluate a particular site. At one time, we thought that was the way to go. Now we're finding out that deep learning has changed all that. And there's many other things that people want to do with this, but and it will happen. So let's go down past this. You can read that. Well, I think I can get past this first. Yes, there is. Now, sometimes when all these kinds of things happen, you find that some people, especially science fiction writers, will tell you that we're approaching a singularity. This is supposedly the point where computers become smarter than humans. I heard Roy Kurzweil talk on this at URI several years ago. He thought that we were practically there. We were going to have it in, a few years. I don't think so. Many, many people don't think so. I'm not afraid of that at the moment. Now, in a game, the usual idea is that each position of the game is a node, and the position has successes. What position you go to if you make a particular move in that position. So, for example, in chess, there are 20 first moves that white can make. He can move any one of the 8 pawns, either 1 square forward or 2 squares forward, and he can move either one of the 2 knights to 2 different places. And of course, after he makes that move, black can then make 20 responses. So 20 times 20 is 400 already. And we're just finished move 1. Now, the way we look at this is we talk loosely about a game tree. The problem is that the word tree is problematic. A tree has no cycles. We're not supposed to be able to come back to something we left by just going down the tree. But positions keep repeating in the game tree. So the more proper title would be it's a game graph. But we look at it as a tree, and we basically try to avoid duplicate positions if we can. Now, I looked at, just as a rough example, I thought we'd look at tic-tac-toe. I think I'm absolutely convinced no one can win at tic-tac-toe unless the other side does not know how to play the game well. It's a draw. But we could represent the initial position as 9 characters, and they start out all as B blank. You know that word capitalizes the first variable, first character in a sentence, so I just left it there. I didn't feel like fixing it. Now, what are its children? Well, it has 9 children. Every one of the positions we can move to as X. So there are 9 possibilities that we can get to from the first position. Then, if we look at just this one position, it has 8 children. So each of the 9 positions has 8 children. We're at 72 positions already. Whenever you play a game or write a program for a game, you have to have a successor function. This is a function where if you put in a position, it gives you back all the positions that you can reach in one move from that particular position. You also usually have to have an evaluation function. Now, again, I said that with deep learning, there are other ways of doing this. But for years, we usually had an evaluation function, and we would get that evaluation function by getting an expert on the game to tell us how they evaluated the position. For a tic-tac-toe board, I looked this up on the web. One possibility is count the rows and the columns where X still can win. That is, where the row of the column or the diagonal, one of the 2 diagonals, has nothing on it but blanks and X's. It's one possibility. I don't know how good it is, but it is there. Sometimes, unfortunately, there's a move that has to be made. If your opponent has 2 in a row, a column, or diagonal, and the third one is blank, you have to make that move. Usually, we like to evaluate the position from one person's side. And we view the idea is that what's good for the first player is bad for the second player. So the first player, that player should be trying to, we'll decide that the best score is the higher score. So the higher your evaluation function, the better it is for the first player. But that means the worse it is for the second player. Now, The rest of this I'm going to cut out when I send this to you because I want to do it a different way right now. Now here is an example of how we work this. I'm going to pull this over. Well, I hope I'm going to pull it over. Here it is. Here we are. That's what I want. Now I can move that up a little. And I cannot quite get it all within the screen. There it is. I think I got most of it in there now. You're just missing a slight little piece on the... There, I've got... well, I still can't get the last value in. This is a typical game tree. What I am saying is that we are right here at the top. We are trying to maximize us. We're the maximizer. We're the first player. All the valuations will be from our view. Now, to make it easy, I said that in this position, we have 3 possible moves. So when we move, we could go here, there, or there. And now the min player makes a move. The minimizer is the second player. He wants low evaluations. So in each of these 3, the minimizer has 3 moves. So think of this as move 1 for the first side, move 1 for the second side, move 2 for the first side. Now the question is, how far down do you go? To make life easier, I just went down 3 levels here. It's obviously not enough, but I just thought we'd manage that. At the bottom of a game tree, or as far down as you're going to go, you apply the evaluation function. So the leaves of the tree are where the evaluation function is. And now your job is to figure out which one of those 3 moves you should make. So let's look at it and try to do it logically. If Maximizer makes this first move here, excuse me, I want to bring up something. Well, I can't. It won't come up. Yeah, there it is. You don't see it, but that's okay. It's the way I can play around with these. Maximizer makes a move. Minimizer then chooses his move. Now, the minimizer looks at the 3 moves it has. It says, I have 5 if I move this way. I have 6 if I move that way. There is an 8 if I move that way. So it seems to the minimizer that he wants the lowest score. So the minimizer is going to say, well, that move value is 5. It's the worst. It's the low score I want. I don't want the high score. It's hard to make these big enough to see, but I'm picking the 5 because that's the one that is the lowest of these. Now I come over here and look at this next item. Well, this is a good one for the maximizer. He can get a 9, a 10, or a 6. Unfortunately, the minimizer is going to take the 6. So the value is 6. Because the minimizer is not dumb. He's not going to take the one that gives his opponent the best chance. He's going to take the one that gives him the best chance. Next, we look at the third possibility. Well, this is a 5, a 6, and that's a 7, although you can't see it. Well, obviously, the best thing for the minimizer is to take the 5. So the value there is 5. Now we look at the maximizer at the beginning. If the maximizer moves, his opponent has 3 possibilities. One gives an evaluation of 5. One gives an evaluation of 6, and the other one gives an evaluation of 5. Well, the minimizer isn't going to choose the middle one. So the value up here is 5. And the maximizer will decide, well, I'll have to take whatever I can get. If I make a move, my opponent's going to make a move, and I can't force him to make the move I want to make. Actually, I think I'm wrong here, pardon me. The maximizer will take the middle move because he determines which one of the 3 moves is going to be made. So he looks and says, I don't want to make the first move because the minimizer would pick a value that would only have 5 in it. He says, I don't want to make the third move. The minimizer would pick the value 5. But if I make the middle move, the minimizer has to choose between a 9, a 10, and a 6. The best the minimizer can do is take the 6. So the maximizer is going to go for that middle move. It is better than the other 2 moves. Now, this is the beginning of talking about this. Actually, the problem is it explodes too fast. There are too many moves. There are ways of pruning the tree. These are called alpha beta cutoffs and minimax. What I'm going to do is talk about them in our next video, which may be tomorrow or may be a little later. So that's it for now. I hope to see you soon. And if you have any questions on the homework or the essay that are due, let me know. I'll see what I can do for you. I did extend, I think, the due dates are there. So try to do the best you can. And again, let me know if you have any problems. I'm willing to set up one-on-one Zoom sessions or Zoom sessions with several people, whichever you prefer. Good night now.